Welcome to Building Robodoc, an idiot's guide to artificial intelligence in healthcare. Welcome back. So in the last podcast we began to talk about the difference between conventional computer programs and AI, or machine learning. So in the former, you have to give the computer an exhaustive set of instructions explaining how to perform a task. In the latter, you show the computer the task you want it to perform and, with the help of a few very clever algorithms, you let it figure out things by itself. Now this might seem a little abstract, so let's take a look at an example and make it a bit more concrete. We'll take our example from the field of computer vision, by which we mean the ability of a computer to look at an image and make some sort of sense of it. So this often means identifying one or more objects within the picture and possibly going on to identify their boundaries. To us humans, this seems like an absolutely trivial task. If you show someone a photo and ask them if that image contains, say, a cat, they're going to give you a correct answer within just a second or two. The trouble is, if you then ask them to describe exactly how they formulated their answer, they'll be stumped. In particular, imagine trying to explain how you can look at both a front-on, close-up picture of a tabby cat on a cushion and a side-on distant shot of, say, a Siamese leaping between the branches of a tree, but you can immediately identify them both as cat photos. Although you know that in real life those cats share many physical features, the pictures themselves of these cats have almost nothing in common. This peculiar failure to explain how we perform the most trivial of tasks arises because visual processing takes place at an almost exclusively subconscious level for us, and much of the work's actually done by the brain's occipital lobes. Here's what seems to happen then. At any given point in time, a massive number of photons are hitting the photoreceptors on our retinas at the back of our eyes, generating lots of electrical signals that travel in parallel along our optic nerves, and they're passed into the extraordinarily complex network of interconnected neurons when they get to the occipital lobes of the brain. We don't quite understand exactly what happens when these signals pass through these so-called neural networks, and by the way, remember that term, we'll come back to it later, but somehow an enormous mass of irrelevant information gets filtered out, and the remaining meaningful information is translated into the kind of abstract concepts that our conscious brains understand. So, house, bicycle, cat, etc. And these messages are forwarded onto our cerebral cortices where we can use them. All this is kind of amazing, I think, but the take home right now is that we cannot write a step-by-step set of instructions in computer code explaining how to perform this feat of data processing, because we don't consciously understand it for ourselves, so we can't articulate it. For a long time, this was enormously frustrating for computer scientists, because human-level computer vision is absolutely vital for a wide range of really useful applications. So think Google image search, think self-driving cars, and someday we're talking about autonomous robots. Now, machine learning changes all of that. Let's go back to the cat from earlier. Let us in fact say that we want to create an artificially intelligent computer application that can look at any photo and tell us confidently whether or not it contains a cat. Here, in broad and sweeping terms, is how you might do this. To start, you acquire loads of pictures, some of which contain cats and some of which don't. And by loads, I do mean thousands and thousands, if not millions of pictures. And then you go through every single picture and label them. Label them with a 1, as in the digit 1 for cats, and a 0 for no cats. So this is a bit arduous, but it'll be well worth it for your wonderful cat identifying machine. And by the way, this is actually how things are done for some tasks in the real world, and often the labeling task is outsourced to perhaps places where labour is a bit cheaper by the likes of Google or Netflix or whoever's doing the labeling. Anyway, that's by the by. Next thing you do is you download the data from your images into the computer where you're making your program, along with the corresponding labels for each image. Remember, 1 for cat, 0 for no cat. At this point, it's important to note that the computer sees an image as a matrix or a grid of numbers, just like in the Keanu Reeves movie, The Matrix. The numbers in the matrix, just incidentally, represent usually the red, green, and blue values of each individual pixel in the image. So you have sort of 3 layers of grids of numbers. Anyway, don't worry about that bit. Next, what you do is you get your computer to come up with a completely random series of calculations that will allow it to take the matrix of numbers that represents each image and output just a single real number. And in this case, we want it to be between 0 and 1. Just in case you're struggling to visualize what I mean by calculations that will take you from a matrix of numbers to a single number, imagine I wrote down 100 different numbers in a grid shape on a page and asked you to just come up with some random way of combining them all together. I mean, you probably just go along sort of, left to right, top to bottom, the same way we read words, and you'd stick in plus, minus, multiplication, division signs between each number. And then at the end, you'd write an equal sign and you'd go through all the sums that you'd written down. So that's a really oversimplified version of what the computer does at the beginning of a machine learning cycle, but it at least gives you the idea. We take loads and loads of numbers, we find a way of combining them all together and through random calculations, and it gives us a single number at the end. Okay, so now you get your computer to put every image matrix, because remember, to a computer, an image is a matrix of numbers, you get it to put every image through this random set of calculations. So let's say you had 10,000 sample images, either containing cats or not containing cats. By the time you've put all those 10,000 images through your random set of calculations, you'll now have a list of 10,000 single numbers. And remember, we asked the computer to make sure they're all between 0 and 1. So we got 10,000 fractions between 0 and 1, just all in a long list. Next, you get the computer to compare this list of numbers with the list of actual 0 or 1 labels you made earlier to denote whether or not each image contained a cat. The difference between the two lists is called the error, because ultimately what we want the computer to do is adjust these calculations so that these lists match up as closely as possible, so that the numbers, the list of 10,000 numbers your computer churns out matches up with the list of 0 or 1s that some human has painstakingly made by going through each image and saying whether it contains a cat or not. Of course, after the first cycle of this process, the error will be huge because all the computer's done is taken a random stab in the dark at putting these numbers through completely meaningless calculations. Okay? Now, I know so far this has been all a bit dry, but here comes the clever bit, so stick with me. The genius of machine learning algorithms is that they can take this error, the difference between your randomly generated list and the actual correct list, and these algorithms work out how to make small adjustments to all those random calculations your computer's generated in such a way that next time all the images are put through these once random calculations that have now been adjusted, the error will be just a little bit smaller. If you're big into mathematics, it's all to do with taking the derivatives of each calculation with respect to its position in the computing graph, and from there you can work out to what extent each calculation is likely to have contributed to the overall error, and you can work out how much to change it. But if you're not into big maths, if you're not big into maths, forget I ever said that. It's not important. The important thing is the improvements to the calculations might only be tiny with each cycle of the learning process, but the fact the calculations do improve each time, rather than just getting randomly adjusted with each cycle, is the key to the whole process. Without this constructive change that allows the calculations to improve each time, it'd be the equivalent to that analogy where you put an infinite number of monkeys in front of an infinite number of typewriters and one of them will produce the full works of Shakespeare. You would need huge numbers of stabbing in the dark before you came up with anything meaningful. So the key to machine learning is that each time you run over a cycle of machine learning, you make small constructive adjustments using some very, very clever maths. So after that, you simply get the computer to repeat this cycle of improving the calculations slightly, re-evaluating the error by putting all the images through these new calculations and then comparing the two lists, and then it'll go back through and make slight improvements again, and you do this thousands, if not millions of times. Now, this might take a while for some applications, and this, by the way, is the reason that AI, the dream of AI, wasn't realized until very recently, even though the theory existed maybe 50 years ago, because we didn't have the raw processing power to make it happen. But eventually, you'll find that you have a series of calculations that are no longer just random, but they've been adjusted bit by bit by bit, so that the computer can now take an image, remember, an image matrix, technically speaking, and it can take this matrix of numbers, put it through these calculations that have been adjusted millions of times, and what it will produce is a list of numbers that are very, very close to the actual 0 or 1 labels that are human made for each image. And in fact, if you round your computer's results off, because it'll be producing numbers like 0.997 or 0.001, so you have to round the numbers off to the nearest 0 or 1. But if you do go through and round them off, you might expect as much as a 99% match between these two lists of 10,000 numbers for a relatively simple image processing task like this. And for this particular task, the cat or no cat task, I mean, it might only take a few hours for your computer to run millions of iterations of the learning cycle, because we have such massive amounts of processing power available to us in our desktop computers and even our phones these days. Right, so that was pretty heavy duty. Hopefully, this is one of the most heavy duty presentations in this series, but up until this point, it may seem like we've run over a lot of slightly pointless mathematics. But here's the incredible thing. If you now give the computer a completely new image that it has never seen before and did not form part of the training set, it could take this image, put it through those same calculations that it's been adjusting bit by bit by bit by bit during the training cycle, and by running this new image through those calculations, it will generate a cat or no cat label that's almost certainly going to be correct, because it's now got a very high level of accuracy. So what you've now found is that a computer can see, in inverted commas, cats pretty much as well as a human can. And this, of course, is despite the fact that we have told the computer absolutely nothing about what cats are, what they look like, or how you identify them in a picture. It's just completely worked it out by itself from this starting point of a load of images and the end point of a load of labels that are humans made. So this that we're talking about is a process called supervised learning, because a human has been through and labelled all the images. So a human has expertly performed the task that we want the computer to perform loads and loads of times. And we gave the computer a load of examples of this task having been expertly performed, and we asked it to imitate the human, basically. So it's supervised learning. And it's also probably worth saying that what I've had in mind when I've been describing this technique is specifically something called a neural network that's being tweaked with a process called gradient descent. I should note there are other mathematical techniques, many of them in fact, for formulating a set of calculations that will get you from source data A to outcome label B. But really don't worry about that. I'm only putting that in as a technical side note. And just to summarise, because I know it's been quite detailed, to summarise what happens during this process is that the computer takes an initially random set of calculations, and through lots of cycles of trial, error, and incremental improvements, it refines them to the point where these once random calculations become a mathematical description of some sort of complex knowledge. And this is often knowledge that we humans are unable to overtly express. It's tacit knowledge, like what makes us able to identify two completely different looking cats from an image as both being cats. Now, this might not seem very intelligent in inverted commas just now, because the cat no cat example is great for simplicity, but it doesn't necessarily inspire a sense of awe and wonder. We're not going to achieve very much with an application that could tell us whether or not there's a cat in a picture. So to try and really recapture some of the magic of machine learning, artificial intelligence, and the incredible things we can do with them, in the next podcast, we're going to get into self-driving cars and look at how this same theory can be applied to that field.